Oh, really?
I can.
Okay, welcome. Today we'll be talking about design principles, but quickly first we'll review the main content of the previous lecture. So last time we talked about marks and channels, and like what are marks and channels? Marks are these things that represent items or links, so that essentially represent our independent variables. And then the channels can change the appearance based on an attribute. So like essentially channels encode data about the items. And channels are often also called visual variables. And so we distinguish between a couple of different marks based on fundamental geometric elements. So there were points, lines, and areas. And you could also use volume, but in practice that's rarely used. And for links, there's other types of marks that would be like containment, the shapes, or connections. And the channels, in turn, they control the appearance proportional to or based on an attribute. So we discussed position, shape, size, area, volume, tilt, and also color. And so if you remember, we distinguished two types of channels. We distinguished magnitude channels and identity channels. So magnitude channels are essentially useful for asking questions like how much, for anything that is, for example, numerical data. We use position, length, and saturation for this. So like ordinal and quantitative data falls in that category. And then identity channels is what, where. And so here the standard channels are shape, color, hue, and also spatial region. And so we have this classification. Not every channel is equal. They have different qualities, and so this is an ordered list. So we have position on a common scale as the most important channel, and then we go through length, through tilt, area, depth, 3D position, and then color luminance, color saturation, curvature, and volume. So like basically what you should do is you should use those first, and if you cannot use them for whatever reason, then you should go to the next one in line here. Identity channels for categorical attributes is like the best one is spatial region. So that is, for example, commonly used in bar charts. Like we have one bar per category. Color hue is possible. Motion and shape. Motion, however, is of course tricky. And just to review the most important ones, position is the strongest visual variable, and it's basically suitable for all data types. So you should always use it unless it's not available because you have spatial data in the first place, like maps, for example, or volume renderings. And it can also lead to cluttering. So if I have a lot, for example, if I just did, if I had like one region where 97% of my data is, then maybe this isn't the best way to encode this as a scatter plot. Length and size are good for 1D, okay for 2D, and bad for 3D. And then we distinguish between length when we have alignment. So then it's actually like a redundantly encoded position and alignment and length. Or if we have unaligned bars, so like here for example, or if one of those is tilted and so on. So length is a good indicator, but it's not as effective as position. Then value, luminance, saturation are okay for quantitative data when lengths and size are already used, but we're not really able to recognize too many shades of gray. Color is not used for quantitative data, like you shouldn't use it for quantitative data. It is used for quantitative data quite a bit, unfortunately. It is good for qualitative data. We have a limited number of classes, so we can essentially like safely distinguish 7 or 10 colors. Of course, if they're close to each other, we can distinguish more, but if they're in different places with some distractors in between them, it's hard for us to distinguish more than 7 or 10 colors. And we had a lot of rules about, like, we learned a lot about colors that was in the perception lecture. So my personal rule, my design rule is minimize color use for encoding data and use color for brushing, for interactive highlighting, for some supplemental information. Shape is great to recognize many different classes, but it doesn't have any grouping or ordering. So typically, shape isn't super useful unless like you can do different mark shapes in scatter plots and so on. And so this was the Stevens psychophysical power law that essentially tells us the relationship of how we perceive something and the intensity of the physical intensity of the stimulus. And so the power law is S is I to the power of n, and ideally we would have like physical intensity would exactly correspond to perceived sensation, and there's only one of those visual variables where that is true, that is like length position. And all of the others here, like brightness and depth and area and so on, are either smaller than 1, so we underestimate them, or bigger than 1, and so we overestimate them. And then we talked about other factors affecting accuracy, and I already mentioned this a bit, but alignment is of course important, then context, giving people like framing is important, and then like the number of distractors. For example, it's easier for me to compare those two bar charts to each other than those two, or something where I have like these long distances. So here it's really not so easy anymore to pick out which one of those is the longer one. Okay, so that was the quick recap on marks and channels. Any questions about this? Yeah?
Frequently with quantitative data, they use color, but in combination with saturation, and that's I see it the most common. So, but you don't really have a category that combines the two. So the red-blue jet scale, for example, on MATLAB is probably the most.
Well, red-blue is okay because it's kind of a divergent color scale, right? So you assume, like for example, a multi-hue color map. If you have a diverging scale, then it's fine. If you have a meaningful, like a center point. So what is like done in genomics quite a lot is these red-blue heat maps, and here you have like this is always you have to think of this as relative to another experiment. And so red means it's higher than the other experiment, blue means it's lower than another experiment. So if you have these relative to encodings, then it's a good approach. If you just like have one continuous color scale and use this red to blue, then it's usually not the best idea. It's not like, and so it's kind of like an open research question why people like rainbow color maps so much. And my colleague Mariah Maya has the theory that they like it because they actually like binned color scales. Like if you remember, we had, like I showed you this picture of a map with elevation binned, and so they did research for that on grayscale. And so their theory is that people like the rainbow color map because they have discrete bins and can like easily pick that out. But then kind of the extension of that thought is that if you design these bins more carefully, you could make relative judgments and have the utility of the binning. So it's like hotly debated. And all of what I'm saying here is, of course, like guidelines. There are always situations where like something can work out in your specific circumstances. But we'll be talking a lot about guidelines today, and then maybe if we still have time about tasks. But at the end of this class, today I want to do like another design critique, but this time not only design critique, but also a redesign. So you'll be sketching a couple of different designs, and then like trying to improve a visualization. Okay, so anything administrative? Today is there's a lab starting when?
So it starts at 3:30.
3:30.
Web 1248. So classroom.
Yeah, Web 1248. There's a lab that reviews homework 4, how you can tackle that problem. And then there will be another lab next Tuesday after the lecture where we review homework 2 and 3, like where we go through the solution for homework 2 and 3.
And then the homework, the office hours today, usually is 3:30 to 5:30 because we're doing the homework lab the first hour. My office hours will be the second hour in that
Okay.
same room. So
Same room. So you can stay around and have Health Carolina explain everything to you once more. Okay, Design guideline. The rule number one, and I've hammered it home, I guess, in the last lecture, and this, I'm just going to rephrase it here, use the best visual channel available for the most important aspect of your data. So think about what do you want to say, and then use position for that. And if you cannot use position, then use the next best thing out there, like length. And when you cannot use that, use luminance, and so on. But let's keep that aside for now. There is a good book that's storytelling with data, and that is not a visualization research book, but it's a book that essentially covers what I'm talking about in this lecture in detail. It gives you like very practical advice on how to build good charts. It's not about building interactive visualization, it's about how do you communicate your data efficiently, mostly in a static format. So this is like journalism or reporting and so on, but it is a good book, it is well designed. I have a couple of examples from this book in the slides here, so I definitely can recommend it if you're interested in these design guidelines and how to essentially communicate your data. Most of the things that she introduces in this book is actually possible to do with Excel, and most of the things that we'll be talking about in the rest of this class are definitely not possible with Excel. So that's why I say it's not a visualization book, but a charting book. So when we talk about design guidelines, there is no way to get around this person. Edward Tufte, he was a, I think, Princeton statistics professor, is now retired, and he has essentially been like one of the founding fathers of the visualization field. And he has published these 4 different books. And so this is, like, these books are a great curation of examples, of historic examples. He gives them like a lot of consideration. So you essentially, if you read those books, you go through like 1 million case studies. And they're really well made. He also teaches courses that are super expensive and not worth going to. So he has done some great things for the visualization community, but he's become a little bit of a grumpy old man. And so he teaches graphical integrity and excellence, but he's not a, like, okay, so, well. So he, like, one of his statements is about design excellence. Well-designed presentations of interesting data are a matter of substance, of statistics, and of design. And so here is an example of one of his works. He's kind of the inventor of spark lines. These are just little line charts. So this is like a very recent example where the New York Times uses them to show you how the race has changed in these various states according to the polls, the presidential race. So you can see like that Trump has gone from 29% chance of winning Ohio to 56% chance over like a certain time period. And these are like what's called small multiples. So that's one of the examples of the things that he's done. And he would hate me for putting the trademark symbol up there, but they're not trademarks. Yeah?
I don't know if you know about this, but through the English department, they have a visual writer class, and they cover his beautiful evidence of semester.
Yeah, okay. Well, there's Tufte is really like design guidelines. And I recommend really, if you want to get the gist of everything, this book is like more efficient to read and more, let's say, more practical. In Tufte's book are a lot of examples and they're less organized. Like he gives you a picture and then writes about it. And this one here really thinks about, okay, how do we get started and so on. So there's more structure in this book. He's also like an evident hater of PowerPoint. So this is what I've got from Twitter every time you make a PowerPoint that Tufte kills a kitten. So that's why I'm ranting a bit about his courses, because he's not teaching visualization for most of them. He's just making you write text and never use ever PowerPoint. Okay, well, but still, he has contributed to the field, and I'm gonna like teach a couple of the things that he primed for this field. So one of the most important principles in visualization is the graphical integrity. The magnitude in the data must correspond to the magnitude of the mark. So what's wrong with this chart?
They've cut off the most of the bars.
Yeah. So it looks like, and Fox News, we'll have a lot of Fox News examples in this. A completely unbiased view, obviously. So if Bush were to cut tax, if the Bush tax cuts were to expire, we would suddenly pay 5 times as much taxes, is what this chart tells you. But if you look at the labels, it actually is not true. It's from 35% to 39.6%. So they have arbitrarily cut this axis. And that is like, here the magnitude in the data does not correspond to the magnitude of the mark. So we'll be talking a lot about how to choose your scales today. This is if you did this chart honestly. Like if you showed it from like a neutral zero axis, and you can see that this change, of course the numbers, it's 4% more, that was correct here, but the perception is very different. So this is another chart. This is an Austrian newspaper, which is like the Austrian tabloid. About 50% of all the households get it delivered to their homes. And this is about social security that is being paid to foreigners. So you can see that they're trying to essentially say, oh, all of these foreigners, like from Turkey and from Serbia and from Syria, they take away all of our social security. And so the first part here represents the Austrians. And then the second part here is some like other countries. The third part here is Turkey. And so what they're telling you is essentially that Turkey and the other countries, they're taking up all of our social security. So what they're not doing is, they, like, you might see it here, they clip the bar. So for all the Austrians that get social security. So this is what the bar would really look like, but it doesn't even fit on that screen. Oh. This is what the bar really looks like. And still, this is on the, like, in this newspaper, in this Austrian newspaper, and clearly there is a message, and clearly they don't want you to see this chart, and because it completely reframes the message. And sure, the numbers were written in here, but not the visualization. The visualization didn't show it. Another even more blatant one. So here. In this case, I don't have to comment the thing. Here we have an interesting scale distortion. So if you look at this chart, what's wrong with this chart? Yeah. So it's essentially job loss by random quarter. I think there would. Yeah. So there is a somewhere. Anyways, there, like, if you look at this spacing between the times isn't uniform. So it's simply not a fair depiction of this scale. Then one question is, should you always start your scales at 0? So for example, if you see a chart like median household income in 2010, inflation adjusted dollars, if you show it not zero based here in blue, then it looks like a lot has changed, right? It looks like we see the ups and downs quite a bit. But if you use a zero baseline, you can see that these relative changes are pretty small. So some people teach that there is a golden rule that you should never cut off the scales of a bar chart, but you can actually do that with line charts. And I'm saying it doesn't matter whether it's a bar chart or a line chart. You really usually shouldn't cut off your scales at any point. There are exceptions, but then you should be very explicit about what you're doing. So of course you see the differences, you see these trends here, but you're kind of overemphasizing the effect that we actually experience. So an alternative to doing this would actually to plot, instead of plotting the absolutes, you could simply derive the difference and then plot the difference instead. So here's a little video.
We make a lot of charts at Fox.com. And of course, charts have axes. And pretty much every time we run a chart with a y-axis that starts anywhere other than 0, someone winds up emailing to complain. You see, there's a really famous book called How to Lie with Statistics, and it contains a discussion of how you can create a misleading chart by messing with the y-axis. And it's definitely true, you can do this. Here's a chart from Fox News, for example. It's a total disaster. But the y-axis dogmatists take it way too far. The big problem with the people who lie with statistics is that they're lying to you. It's true that misleading charts are one way to lie, but the English language is also a tool that can be used for lying, and that doesn't mean we should never speak English. sometimes you need to fiddle with the y-axis to tell a story properly. So for example, right now, the share of American adults who have a job has fallen to a generation-long low. It's a really big deal. But if you chart this data with the y-axis at 0, you can't see the change at all. Narrowing the range to dramatize what we're talking about isn't lying with statistics, it's emphasizing what's relevant. The way Edward Tufte puts it is you need to use a baseline that shows the data, not the 0 point. And after all, 0 is just a number, like any other. Sometimes to make sense of the data, you need to be able to show numbers that go below 0. Halting at 0 in those cases doesn't make any sense, but extending every chart way below 0 would be crazy too. And of course, where 0 even is depends on the units you're using. If you do a chart of a person's temperature in Fahrenheit, you're likely to miss the fever if you zoomed all the way out to 0. If you redo it as a Celsius chart, it's not quite as bad. But if you switch to Kelvin and extend everything to absolute 0, then the charts become useless. When people are really lying with charts, the main thing they're normally doing wrong is leaving out the context, not leaving out the 0. Go back to that Fox News chart. You'd never know from this chart that the top marginal rate was 39.6% back in the Clinton administration, or that the Reagan administration was 50%, or that back when Eisenhower was president it was 91%. The missing 0 was really the last of that chart's problems. What they left out was the entire history of taxes in the United States. So just remember, y-axes don't lie to people. People do.
So yeah, this is a great summary of the subtleties. And so this kind of also leads us to this, visualization is often considered to be like a wicked design problem. So it's hard to get, like, there's no one solution, there's no perfect solution, there's no best solution. You kind of like, what you try to achieve is, when you create a visualization, is something that is faithful and that solves a particular problem. Here's another example. If you looked at this chart of temperatures, global mean temperatures from 1997 to 2012, it looks like, okay, nothing is really going on. Then if you start reframing this in like the larger scope, then you see that there's actually quite a lot happening. And so some of you might have seen, I actually forgot to put it in the figure, but some of you might have seen the nice XKCD chart recently, where he visualized how the temperature has changed in the last couple of thousand of years. And there you can clearly see what is going on with climate change. So context and framing is really important in visualization. What's wrong with this chart? 55 and 54, yes, so we don't have a neutral baseline, but there's another thing wrong.
The years are out of order.
Yes. So if you plot time linearly. So there is no reason of plotting 2012, 1999, 2013. They're simply like, people will always be fooled by that. If you plot time, it needs to be in order. And in, but yeah. So this is actually the other chart. I don't know how that happened, but this is the chart that shows the unemployment according to the by the right quarter. So here we actually have this one big jump in 2008. It's not by it's not a linear trend. It's this trend with these extremes here. Yep.
So looking at that reminds me of another thing that I've had issue with a lot of charts, and that is connecting points when you have no data in between, because people are going to automatically take those as data, even though it means nothing.
Yes, that's a problem, that again is a design decision. And at what point, sometimes it is a fair assumption. You have a continuous, time is continuous, right? And you cannot measure continuous. You cannot plot these things continuously. So you have to do some kind of sampling. And what kind of sampling? That is often tricky to do. The best way of doing it is to simply look at, well, if you have the data, look at it and then do the right sampling. But if you don't have the data, it's difficult. There's of course approaches for linear interpolation or other more sophisticated interpolation methods, but it's not there's no answer for everything. So this chart here is really bizarre. This shows is an actual visualization that I found on the internet. It's Republican Party presidential primary schedule in 2016. the day of the month is encoded here as the height. The months are encoded as color, and the states are encoded on the x-axis. And now try to figure out when which primary is. Of course, all the data is there, right? This faithfully represents the data, it doesn't lie. It's just one of the worst charts that you could actually come up with.
They just point in text out and all good.
Yeah. So this is another things of the, like another of these concepts, these Tufte terms, is the lie factor. It's the size of the effect shown in the graphic divided by the size of the effect in the data. So this is like an old newspaper chart from one of Tufte's books. This is fuel economy standards of autos. And so here we have a line that represents 27.5 miles per gallon. And this is 5.3 inches long. And here we have a line that represents 18 miles per gallon and is 0.6 inches long. So they kind of use this perspective distortion here in a wrong way. And so you can actually calculate the lie factor. You can say in this case, the lie factor is 14.8. So size of the effect in the graphic and size of the effect in the data, and you of course want this to be 1. Another example from Tufte's book, we have here what is happening is again this problem of area versus height. So we have the shrinking family doctor in California, where percentage of doctors devoted solely to family practice is 27% in 1964 and 12% in 1990. So like, it's like it's simply misrepresenting this change quite a bit, because this doctor doesn't look like a couple of percent larger, he looks many, many times larger. And then here for volume, that is like a similar problem, oil prices per volume. And so we have these massive changes, we have these volumetric representations that simply do not match the data. So Tufte's integrity principles is about showing the data variation and not the design variation. It's about clear, detailed, and thorough labeling and appropriate scales, and that is like a common beginner's mistake to not include the labels. So we, like for example, in many of, like I've taught this class before, and many of the projects show some data, but they don't actually label what is going on. So that is like a common problem. And then the size of the graphic effect should be directly proportional to the numerical quantities. Like if it's not, we have this lie factor to quantify it. So the next 5 minutes are going to be a rant about pie charts. There is like a lot of contentious discussion about whether pie charts are good or bad or not. And so generally my advice is not to use them too much. Pie charts are really useful sometimes to show parts of a whole relationships, but it turns out that you rarely need to communicate these parts of a whole relationship explicitly. So what is wrong with this pie chart? So we use so many colors, like social networks and e-commerce, for example, are hard to distinguish, and then we have another one here that is repetitive, so the colors are not unique. And then we don't even see what those little slices are up here. So a pie chart with very many slices is often problematic. And so here is a slightly better pie chart where we kind of like don't have these repetitive colors. But you could also visualize this as a bar chart. And like, do you think really miss the information that if you add all of these numbers up, it's 100? I don't know. I personally don't think so. However, if you make pie charts, make sure that they come up to 100%. That they really show the whole. There's also bar charts that show everything in the pie, and they come up with 97% or with 103%, and so on. So take a look at these charts and try to understand like what is the relationship between the black bar, how has it changed between A, B, and C, and all the other segments. So any trends that you can see here?
Black is getting smaller.
Yeah, black is being smaller, red is
Slightly increasing.
okay. So we can plot the same chart here as a bar chart, and we can see like much clearer what is actually going on. So we have these relationships that were essentially like red, blue, green. Like I personally didn't see that green is like slightly bigger than blue and so on. So it's much easier to perceive. Again, this goes back to this visual channels. We know that position is easier to perceive than angle. And so here we have an upward trend, here we have like a roughly stable trend, and here we have a downward trend.
So pie charts could be good if your goal is to hide some of the differences.
Wow. That is, if this is your goal, but then there's other means to do that, right? But so yeah, pie charts are rarely like, and there's a variation of pie charts which are called donut charts, which essentially just have a hole in them. They're equal to pie charts. They're not better or worse. They're equally problematic. This is my favorite pie chart. And this is the second favorite pie chart. Pie I've eaten and pie I have not yet eaten. Okay, so what should you use instead? Because that's always like a question, but I want to show this is a proportion of the whole. So here, like this is a great blog post, you should take a look at this. This is like not exact, not accurate data. It's not about what is in the data here, but the idea here is that you did a pilot summer learning program on science aimed at improving perceptions of children with respect to science. And so before this seminar, or before the summer course, like many of the children said they were bored by science. They didn't think great about science. They thought like 40% thought science is okay, 25% found it kind of interesting, and 19% found it exciting. And then post the seminar, like suddenly slides of 38% found it exciting. So the data is really important. This chart shows everything, and you can read everything from it. But I'm going to show you a couple of alternative designs now, how you could communicate the same data. So first, always, if you just have one mission to show, for example, how effective your pilot program was, you could say 68% of kids, simply numerically, expressed interest towards science compared to 44% going into the program. Like this communicates efficiently. Maybe you don't need visualization here at all. If you want to be a little bit more detailed on how these various categories have shifted, you could say, make a bar chart here. So you could say, and so what this guy did here is he took out these two separate charts and integrated them. And so we see that the board category actually went up. So some of the students were really bored by the seminar, but it was only 1%, and not great also. But what really changed a lot is that this okay group, like those people who didn't really care about it, suddenly got kind of interested or even excited about it. And that's something that you clearly see in this particular chart. The canonical alternative to the pie chart, where you can show exactly the same thing as a part of a whole relationship, is the stacked bar graph. So you have this, like the board, not great, okay, not kind of interested and excited. Also notice how the color here is very clearly chosen to like categorize this like the three different bins between like not, I don't care, and I'm kind of interested about it. So stacked bar charts, as we know, are, if the part of the whole relationship is really what you care about, then they're probably a good alternative, but it's also difficult for us to compare, for example, the size of this one here to the size of this one. So depends on your tasks, it's an alternative.
So is that really only useful for these sort of pseudo-ordinal relationships? Because, I mean, it's, on the surface it's categorical, but you have kind of ordered them, like okay is less than kind of interested, but it's better than not great.
Well, it is better if you have an ordinal scale here, because then it's easier to match up the things. If you had a categorical scale here, you would have to use some kind of labeling. So yeah, if you had a categorical scale, this would be better. And the next thing that I'm going to show will also be better. Yeah?
Also, wouldn't it be better for them to like flip it around so that it is easier for you to see that the exact portion of the audience is shown? Here, both of them end at the same line. So
yeah.
So visually, wouldn't it be better for them to start with the exact and go towards both?
So yeah, that's a good point. Actually, like alignment of these things is also something that you could I could worry about, and I actually have an example that it goes exactly to what you're saying a little bit later. And another alternative that is kind of not really commonly used, but is actually often very good, is a slope graph. And so the slope graph here clearly shows us that this proportion of like people who didn't really care and don't really care afterwards dropped massively, while the other two here went up, and we have like a roughly stable trend here at the bottom. So these slope graphs, they're pretty effective, and they're kind of somewhat related to parallel coordinates, which we'll talk about more in the table lecture. Okay, so like fundamental visualization design principles are also like maximize your data to ink ratio. So here, like I'm going to show you a redesign of this particular chart. This is like income of males and females. I don't know exactly what the population was, but it's not so important. So what we could do this chart is we could instead represent it in 2D, and that would make it much easier for us to see the trends and the effects that we have here. Generally, you should also avoid chart chunk. Like chart chunk are extraneous visual elements that distract from the main message. So here we have a chart that is pretty, like there's a lot of like extra grid lines and so on. And so we could redesign this by, for example, taking out these grid lines. They're not very important. We could be even more minimalistic by taking out the background color. We could remove the frame. And then we could even like reintroduce these thick lines here on the bars. So this is like now a minimalistic bar chart that essentially communicates the same data, but in, let's say, a more appealing way and with less chunk around it. There is, however, a caveat about chart chunk that I'll get to in a second. So which of those two here is better? It's better. So there's like two charts. One of them has, like it's about diamonds, diamond prices, and this is a graphic by Nigel Holmes, who is this like famous newspaper illustrator of these classical graphics. And so here we have one chart, and here we have the other chart. Who thinks this one is better? A couple of people. Who thinks this one is better? Yeah, so we're evenly split. If you followed these like minimalistic, Tufte-esque principles, you would make an argument for this chart here is better. And yes, I would agree if you say all I care about is communicating exactly the data and not having anything here. So for example here, we see that this line isn't really straight and so on. But there is actually research that shows us that chart chunk can be valuable. Here's another example. The cost of House and Senate campaign expenditures. I don't want to plot 2016 on here because this goes to 82. So like, the monstrous cost. This frames us with this monster in the background, and here we have the minimalistic, Tufte-esque version of it. And so sure, this chart is precise. It shows us everything it does, and there's research that shows us that these triangles are like less efficient to read than the bars. But then, is it really better? Do we, like, how about like engagement, memorability, recall? Do people remember 5 days later what you wanted to tell them if they've seen this chart? Or do they remember this chart better? Where do you communicate your data better? And so there's a paper in 2011 that did a big study on this. Is there such a thing as useful junk? And so they compared exactly these Nigel Holmes graphics, these famous Nigel Holmes graphics, to these minimalist Tufte-esque designs. And they actually found that there's no difference in interpretation accuracy. There's no difference in recall accuracy after 5 minutes. So after 5 minutes, people will remember them quite as exactly as well. But there's significantly better recall for the Holmes types charts, for both the chart topic and the details of the data after a long-term gap, like after 2 to 3 weeks. And participants also saw a value message significantly more often than in the plain charts. So they kind of emphasize the point, the topic of the data much more. And they were usually rated more attractive, more enjoyable, easier and faster to remember. So this is like an empirical study. It has been criticized quite a lot in the visualization literature, but it's like basically its results are valid and they still stand. There's different viewpoints and opinions on it, but there has also been follow-up research that memorability, there's certain factors that influence memorability. For example, these are human recognizable shapes. So for example, if you put a person or like an animal in a chart without even making it super well designed, people will remember that they saw this chart. There is some doubt about whether the data recall. So those people here claim that they also could recall the data better compared to the control group, but there is some doubt about the validity of these results. So should you always draw monsters in the back of your charts? Well, it depends. Pros are persuasion, memorability, and engagement, and then cons are, for example, if you want to be unbiased, like monstrous costs is in itself a biased message, right? So if you want to be unbiased, then you shouldn't use chart chunks usually. They don't appear as trustworthy. There is an argument to be made that they're less interpretable and they're less space efficient, and they're of course harder to make. As a general rule, don't do any of those things. It's like banana sales, yeah, a 3D bar chart of banana sales with banana in the background. So this is like Excel 98. These don't aid recall, they don't aid memorability, or maybe they do, but you probably remember them. But you don't, like here, the data is simply hard to read. So use chart chunk if you want to in a way that doesn't influence the message. And this one is one of the most bizarre pie charts that I've ever encountered. So like this is the same pie chart a couple of times, just in like tilted in 3D. Yeah, so conviction in England and Wales for Class A drug supply. Okay, so going back to your point about alignment. So this is a comparison of various US politicians by this PolitiFact website, Who Lies More, a comparison. And at the top of this chart here is Trump with 18% pants on fire lies, and then in total combined about 60% with false or pants on fire. So this isn't a bad chart. You can see that Obama here is at the bottom, and Clinton here is at the bottom, Jeb Bush is at the bottom, Sanders is at the bottom, and so like then we have Cruz, Bachmann, Gingrich, Palin. So there's a pattern. But anyways, this is not a bad chart, but you could actually like change the alignment and make it even better. If you say, okay, what I really care about is like, I consider half true to be kind of this point in between that is still acceptable somewhat for me, then you could say, okay, let's align it here by this baseline. And so this baseline, and then we can use symmetry. Then we don't have to make these comparisons between like these parts here, but we can actually look at who is more honest, or who lies more. So like just a subtle design change that you can actually do in Photoshop mode for this chart, but that kind of makes a bit of a difference.
Can you align on the center point of a category?
You could.
So half true, for example,
Yep.
would seem to be a logical cutoff.
Yes, you could definitely do that. That would make sense. So here they started essentially at like this author made a judgment call that half true is good enough for him. You could say half true is, like, you could cut half true in half, and would probably be fair representation. So one of the other principal design rules, and I've said this a couple of times, but I kind of want to reiterate it, is do not use unjustified 3D. Our depth judgment is really bad. So this is like going back to this Stevens psychophysical power law. We can see that our depth judgment here has this n of 0.67. So like the physical intensity doesn't correspond linearly to the perceived intensity and the perceived sensation. There's other problems with 3D. There's occlusion in 3D. Yeah?
Just kind of like a future forward question. Would you say this might change in the future with the technologies such as virtual reality or augmented reality?
No. I think that there is a point to be made for virtual reality in terms of, like, there's a technique that's called billboarding in 3D, where you can have like a flat surface, then you can render something. So like I, for example, had a demo with the HTC VR glasses. And there, like it was an Infobis demo, and so they had essentially like a big screen set up with many different visualizations, but they were all pinned into 2D. And so things like that are definitely doable, and these devices are getting good enough, and then you have the benefit of spatial orientation, because you can remember I put this over there and I put this over there, but the fundamental problems of depth judgment, occlusion, perspective distortioning, lightening, perspective foreshortening, they stay the same. So, for example, like if you remember all these in the perception lecture, I showed you many of those examples where you perceived like this. There was these two cubes. One of them looked wider than the other one, and you perceived the other one as dark, and the upper one here as light. But when you kind of like removed the 3D shadow effect, you saw that they are actually the same color. So, for example, color judgment is way off in 3D because of how we interpolate mentally lighting. So we kind of like adjust for the lighting in our minds. And also, like it's hard for us to perceive the size of some object in 3D. It is better if you have stereo vision, like if you have a proper virtual reality headset, it's better than on a computer screen, so you get some of the losses back, but it's still not as good as judging them on a 2D plane. Another problem with 3D is that tilted text is of course illegible. And so, like about your question, I've had actually like many people came to my office in the past. I want to run a startup and I want to do 3D virtual reality graph visualization. And even like people that, one of them was a senior Microsoft software engineer. He came to my office and wanted to talk to me about how can I actually do this, how can I like create my startup based on 3D visualization. And these things, like 3D and virtual reality, they are great for things that are inherently spatial, like 3D in general, but they're not the solution to data analysis problems that are not spatial. Yep.
So I've seen data visualizations before where they use the 3D relationship to sort of give context. So, but then you can change perspective. So you're looking at it from one perspective, and you can sort of in the background see the 3D effects, and then the visual changes perspective, and it helps you sort of understand the relationship.
Yeah, so that's a good point. So you should all, like take this with a grain of salt. Like sometimes 3D can give you a benefit if you can see like a larger structure. We'll see later in the course. I have another design critique for a 3D chart that we'll find is not really terrible. So there is courses, but the rule here is no unjustified 3D, right? And if you have a good reason for using 3D, and if then there might be a point. But by default, you should assume it's not a good idea, and then you have to convince yourself that it is maybe a good idea. And what you said about interaction is really important for 3D, because like if you want to resolve any of these problems, like perspective distortion, occlusion, and so on, you can only resolve them by interacting with the tool. So if you have like a graph layout in 3D, which is usually not a good idea, but you could do it, and then you can rotate it, and you could reveal nodes that were otherwise occluded. Here is an example that was actually like a paper in one of the best visualization conferences, but it's in the golden age of Infobis, where you essentially just, if you could hack something together, you could publish it. This is a tree visualization that visualizes the relationships between the structures as 3D beams. So here's the root of the tree, and the size here corresponds to the sum of all its children. And then you have other beams attached to it, and so on. And so this is simply a chart that this is just not readable. There is no point in doing this. Just because you can, just because it's possible to render this, doesn't mean it doesn't make sense to do it. Another rule of thumb that you should follow is the rule of eye speed memory. Don't make people memorize, don't make people think, show them what you want to show them. So here's an example. This is actually an animated GIF, but it doesn't work in Keynote. This is fertility rates in Japan and the United States. So we have two different axes here. We have the age when women first give birth, and then birth rate per woman. And you see that like over time, these two curves change a lot with respect to each other. And so here, what you have to do, if you look at this chart, you have to pay attention and then memorize what is going on. And then memorize, okay, in 1960 it was higher here, and then in the like in 1990 it started to flatten out and so on. So you have to really pay a lot of attention, keep track of it, and if you want to compare something specific like 1949 to 1960, you have to rerun it and think about it and pay attention to these particular points and maybe even like hit pause for a second. So what you could do here instead is what's called small multiples. So here, this chart shows all of those years taken apart. Now this is kind of small, right? So this is really hard to read because we have like these many little charts. But the question is, for your tasks, for the question that you want to, for the what you want to communicate, do you really need every single year? So you could say, can we just get rid of some of them and show such a summary? So here we have like the age when giving birth and the birth per women, and you can see that this trend was like in Japan, women gave birth later, but on average probably had more children, which has changed quite a bit now. In the US, women give birth earlier in their lives, and in total have like the sum of the area under the curve, the integration of the curve corresponds to the total number of children per woman. So this would be an alternative, but still, is this chart super effective? No, I think it's better than the animation, right? But you could also think about how can I represent this data in a different way. So what you have to do here is to, for example, understand how many children does the average woman have. You kind of have really to mentally integrate under the curve, which is not easy, like compare the size of these shapes. So what we could instead is we could simplify those charts. And this shows the same data. Those two charts, we say total fertility rate in the US and Japan, and then we say average age when giving birth in the US and Japan. And so here we can see very clearly that what the data shows us, and it's super easy to render. So just an example of like animation is sometimes useful, very often it's not useful. Small multiples are sometimes a solution, but very often it's better to even think more about your data, come up with different designs, simplify, and show really what you care about first. Okay, so next I want to do a design critique redesign of this particular chart here. It's not interactive, so you don't actually have to use it. And you should analyze this, answer the questions here, and then also create a redesign. Here's some scratch paper. Paper? No. Take it as a teams. So if anybody feels comfortable with sharing their design, I'll go around, snap a picture, and show it, and you can explain it. So if you want to do that, raise your hand. share your?
I don't have them like all written out. I can talk about what I think.
Yeah, well, we do that today.
Okay.
Anybody want a short picture? Not all at once. Can I share? Can I share your design? Okay. You want to share your? You want to share your design? Anyone else want to share? Yeah.
I'm willing to share.
It's a nice.
It's not that exciting.
Okay, so let's talk about this chart first before we look at the designs. What's the data that we see here?
The issues that New Zealanders believe are the most important.
Yeah, so it's a survey result, percentage of people who think that these particular issues are important. How is the data visually encoded? Exactly, the categories are encoded by color.
And the percentages by radius.
Exactly, percentages by radius. Does anybody see a problem with that?
Yes, of course. In circles. Using circles and also they are far from each other. Some of them.
Yeah. So like the problem of mixing radius versus the size of a mark, here like for example 14 doesn't look like roughly half of 33, right? It looks a lot smaller compared to 33 here. So we have this, there's this classical mistake of taking radius, diameter to encode your data instead of area. Any other problems that you see with this chart?
I don't see any clear reason to have the unemployment and economy separate from crimes and race relations. Like, they're kind of separate categories of responses, but when you're not going to be showing all the different categories anyway, it's a really arbitrary division.
Yes. You could also reframe this a bit. Like, why do you think are those bubbles integrated with each other? What do you think about that?
Because I think the designers try to imply a certain relations between the two of them. Like, say for example, if people are worried about the economy, but they're not worried about losing their jobs, and like you could argue that that some people do correlate race relations with crime, and that is why those two categories are put together rather than like an arbitrary division.
And what do you think about this particular choice here? Like, I get that they kind of like have a relationship and you want to contrast them, but how about the choices of how this was done?
It would have been better if, like, the relations that we tried to show would have been better if they had encoded in the area rather than radius, which would actually show you that, like what the author is, I believe the designer itself is, in his head, these two things are related, and people are talking about the same thing when they're talking about it.
Mm-hmm.
So it's more like what proportion of people think about the same thing.
Yes.
Also, the most important one goes in the background in this case.
Bigger one, yeah.
Yeah.
Yep.
I think if you want to show the relations and say, well, this category had this many people, it'd be easier to take those circles and rather than stacking them on top of each other this way, stack them this way. Because if you're encoding by a diameter, then the total height is going to represent how many people are in that category, whereas two big circles here include each other, and then it makes the data look like it's half as large for that category.
And so you said something interesting here, this occlusion. There's a couple of cases on here where it becomes a particular problem. Can somebody spot them?
That's really on the top.
Yeah, so here we have exactly the same size, and the visual encoding here breaks down because you wouldn't see the other one anymore. And so this designer had to make like a manual tuning of this visualization for this particular case.
Visualization doesn't say anything about the other choices or what percentage of the total population responded.
Yes, there is context missing. Yep.
I don't know, for me when I was looking at it, I didn't even know what the data meant. If it was something like crime increasing or decreasing, or is it people actually saying what they think?
Yeah, I think just from the label, I think it's people's concern, not actual crime or increase or decrease. But of course, what you can see here is that the worry about the economy increases significantly with the 2008 financial crisis.
I think another thing I was looking at is, so from a viewer's perspective, are we trying to understand like what the actual public opinion is, right? And for that, I think it might be better to visually encoded that if each year had its own scale, because, for example, in 2001, right, it has, or 2008, you can barely see the 1% and then 15, and so you think, oh man, the entire world must really want whatever that is, right?
Yeah.
But then in 2004, there's a bigger gap between those two, but the information is the difference.
Yeah, so what you're saying is that it could be better off if we separated that, or?
Yeah, like the scale was defined for each year instead of having the same measurement.
Yeah.
For the entire thing.
Yeah, that depends on your question, right? So if you say, what are people concerned about overall, then the scale, like keeping one global scale is good. But if you say, how did the perception of this particular problem change over time, then having a scale that is specific to one of these data items is good. So I'm going to show some of your designs. So here we have a line chart. And it looks like all of them are plotted in the same line chart. Who else did draw a line chart? Okay, quite a lot. It kind of makes sense, right? We have years, we have like a clear timely progression, and we want to see them in relationship to each other. So line chart is definitely an appropriate choice here. Then we have a stacked bar chart. What do you think about a stacked bar chart for this case?
It doesn't add up to 100.
What's that?
It doesn't add up to 100.
Yeah, so
It's adding that context in, that's why I like it. It shows overall if people are concerned about other things that are off the survey.
So I would argue that a stacked bar chart could be a good choice, depending on how the question was phrased. If it was a pick one question, then the stacked bar chart has merit, right? If you say, which do you think is the most important of these issues? But if you ask the question like, which are important issues? Then if you have multiple occurrences, then the stacked bar chart wouldn't be a good choice. So I'm not totally sure what the data is, and depending on the data and the task, it could be a good choice or a bad choice. Yeah?
In the same aspect that I think it's harder to understand it's at a glance, it's easy to understand like how it breaks down, but if you wanted to see like what one overall is more popular, I think having bar charts next to each other is more visible.
Yeah, and so changes in a stacked bar chart are, of course, like changes in a stacked bar chart are easy to track for the first element. But then for the second element, like here we can make a position judgment, right? But for the top element here, these are not aligned anymore, so we have to make length judgments. So we kind of like have to use an inferior visual channel to do that. Yeah?
One of the things I do like about this is part of why I chose it, is because now you can group the different categories into what was similar. Just by saying, well, those two bottom sections of the bar were similar, and so they're going to be one bigger bar.
Yes.
I think it would be slightly better if number like category was added, same others, so that it made up to 100. Because without it, the size of the bars over the years would change. So that would add an element that is actually not present in the data, saying that people are more concerned in this year. Like even though like the question itself was the most important problem, so it was. Like,
but you could have an option that I'm not at all concerned.
Yeah, so it needs to have another option of this.
Yeah, so the question is it part of a whole or is it the overall? And that depends on the task, right? On what do you want to learn from it.
So to combat that, I did something kind of similar with where I made it a proportion, so that those four categories all added to 100, and then you could see how it fluctuated.
Yeah, exactly.
Internally.
Yeah, so relative judgments are absolute judgments, and that's it's task dependent. So here we have another line chart, another stacked bar chart, and here we have an aligned bar chart. Is an aligned bar chart a good choice here? Oops.
It's a smart choice if you want to compare the categories themselves.
Exactly. So if for within the year comparison, it is probably the best choice. For between the years, looking at temporal trends, it's probably not the best choice. So like everything is always flexible. So let's look at this. There's somebody else has done a formal redesign of this. So there's the obvious mistake is simply by encoding by diameter, not by area. And so if we encode it instead by area, we see that this looks quite different, especially this here looks quite different. And if we, if you look here, this was basically not visible, the 1%, but the 1% by area is actually quite visible. But is this, like, as you all have realized, is not really the most appropriate encoding in the first place. So you can do just like a line chart, which answers this question here sufficiently. Okay, so this is also the kind of thing, like I think these exercises are really here to train you to critique these designs and come up with your own sketches. And the goal of this is that you kind of think about when you, for example, work on your project, what are really the appropriate visual channels And this is exactly what will also be one of the questions on the exam. Okay, so we have 2 minutes left. I'm not going to start diving into tasks today. So we will meet again on Tuesday. And don't forget, there's the lab now about homework 4.